Um, Hello. Please, can anyone hear me?
Yes, please, we can hear you clearly.
Oh, okay. Then I think we can commence. So with DCIT 203, it is very important that we very much, understand where we are coming from before we can be able to get to terms with what is going on. Okay, this is the whole thing. If you don't take care, you would either get lost from the very beginning or you'll get lost in the middle of the program because DCIT 203 is a continuation or an advancement of DCIT 102, if I have the course code right. Okay, DCIT 102 tackled both digital architecture, okay, that's computer hardware and architecture, and then it also looked at logic and Boolean logic and logic gates, Boolean algebra, etc., etc. So this semester they've divided that particular program into two, okay, into what is now DCIT 203 and I believe 207. Okay, so 203 we are looking at mainly logic gates, Boolean algebra, etc., etc. So this side of things is a little bit technical, and it's very important that you really grab the fundamentals so that we can be able to build on it. So what I realized from our last session with our lecturer is that he's not really doing much about the basics, okay? That's slide one, slide two, slide three, because he considers that we've already done that. So for those who did not very much understand things from where we began from, or perhaps might not really be good with the fundamentals, that is number basis, Boolean algebra, how to simplify logical expressions and those stuffs. You might be found wanting, if not now, in the middle of the whole course because the application of those will become very, very critical along the line. So in order to make this more effective, I would want to first go back, okay, revisit everything from the basics, okay. We are going to use only today for that. So revisit the basics, and as far as we can go, try to hit on some very important things, okay. Freshen our memories and freshen our understanding, okay. And then after that, we can look at how best we can build everything from there. In the next section, I'll try and then have another 203, maybe let's say Friday, okay. Let's see about Friday. That's if that space is granted. You would try and then have a continuation of of that so that we can just zoom straight into the slide. So I think we can start. Please, can you see my screen, please? Um, please, can you see my screen?
Yes, we can see.
Okay. So, all right. So we'll be going back and then, please kindly give me a minute. Okay. I want to Please, can you still see my screen, please?
Yes, we can see.
Okay, so thank you, sir. So I believe we can start. Okay, so I have an empty sheet here, and then I have the slides on another window. So let's start. Okay, so last semester we looked at number bases. Okay, from both DCIT 101, 105. 102, we looked at this very same thing, and under that we did establish some stuff. Okay, please, we'll be going very fast. If you have a question, you can kindly unmute and ask. I think I can't really see the as in the Teams meeting screen. Okay, so that means that if you are to raise your hand, I might probably not see you. So you kindly unmute and talk. Maybe if that's not possible, I think we have some of the admins there, and then they will be able to see you and then notify me to that effect. So please, we looked at a couple of things. Okay, so under number bases, we stated that the basics of number bases that computer uses, or the basic number base that the computer uses, is binary, right? So we looked at binary, hexadecimal, octadecimal, a whole lot, but we said that the basic number system that the computer uses is binary, right? So under this particular, for the sake of DCIT 203, we are going to stick to binary only. Okay, we are not going to look at how to convert binary and those things. No, those things are not very much needed here. Okay, so we are going to look at using binary to directly work with logic gates and all those things. Okay, so we said that binary revolves around the principle bi, right? And bi means two. So when we say bi or binary, we are only talking about two. Okay, so binary revolves around only two unique digits, which is 1 and 0. Okay, so ones and zeros are the only unique digits that we are going to use in all binary numbers, or that we are going to use in our binary numbering system. Okay, so when we take one, okay, it's important to understand ones and zeros in this way, not just as digits, but ones and zeros do hold specific significance, okay, in computing. When we take one represents on, okay, in circuits. One represents on. When we are looking at truth tables and logic gates, one can also represent true. Okay, so these are possible meanings or representations of the number one in binary when it comes to computing and circuits. One can represent on, and one can also represent true. When we take zero, so please, you are going to use this, or DCIT 203 is going to use this simultaneously. Whenever it uses on, know that we are referring to one. Whenever it uses true, know that we are referring to on one. It depends on the kind of context within which it is used. Okay. So whenever you are dealing with truth tables and those stuffs, you use true, false, those things more often. But when we take zero, zero could mean off here. And then zero could also means false. Okay, or in circuit diagrams, zero could also means a state of 0 volts. Okay, so a state where a circuit does not have power actively flowing through it, which is 0 volts flowing through the circuit, is also signified with zero. Okay, so please, this are all possible representations of the number 1 and 0, okay, that are going to be used under DCIT 203. So let's do well to keep these things in our mind, okay? So let me get this thing off the screen. So now we are going to look at our logic gates. So when we talk about logic gates, we looked at this under 102. So we have different types of logic gates, and this are what we use to develop our logical circuit, or this is the fundamental building blocks of our circuits, okay? So we are going to use our logic gates to build transistors, and we are going to use transistors to also build circuits. Now, let us look at the types of logic gates that we have and how they understand this, because understanding this is very, very crucial to the entire course in total, because they will be referenced, but they might not be explained. If you were in our last session with a lecturer, you realize that he did reference this thing a lot, but he did not really explain them. That means he expects that we know them ahead of time. Okay. Yeah. Please, someone wants to say something. Mr. Freeman. Okay.
Sorry,
So, okay. So let us look at our gates. So the first gate that we are going to look at is our buffer gate. Okay. So our buffer gates, but technically we don't call the buffer gate a logic gate. This is the reason why I don't call the buffer gate a logic gate. The buffer gate works in a way that it does not really work with any logic. The only job that it does is to receive an input. Let's call it X. And then when it receives the input, it returns or it outputs the input in the same state as it's received it. It does not process it in any form, okay? So it takes the input X and then returns the output X. So buffer gate basically does not add any other value to its input. It returns the same input it receives as an output. So most often it only accepts one input, and then it returns that same one input as its output. So if you feed it with X, its output is also going to be X. Okay, so in our typical logic circuits, we know that our inputs can be 1 and 0, right? So if the input is 1 for a buffer gate, the output will certainly be 1. And if the input is 0, our output is also certainly going to be 0. So how do we draw a truth table for our buffer gates? So for our buffer gates, we are going to have our input, okay? So let's call the input X, and then we are going to have our outputs here. Okay, so if our input is 1, our output is also going to be 1. And if our input is 0, our output is also going to be 0. So this is the truth table for a buffer gate. Basically, its inputs are the same as the output that it returns. Okay, so we define a buffer gate as a logic gate that passes its input to its output without any change. Okay, in without any value added along the line. So someone might ask the question that why is buffer gate important when building circuits? Okay, you see, there is, I think, if you go back to science, there is Ohm's law. We know that, I think, voltage is equal to current times resistance, right? And one thing that increases resistance is the length of the circuit connection, okay? So if we have a single, let's say, connection being very lengthy, the longer the wire, okay, that flows, as in having a wire that flows freely without any sort of break in it at one point or the other, increases resistance. And and as a result of that, it leads to a reduction in the voltage that flows through that line. So in order to prevent that, what we do is that we create a buffer gate along the line, okay? So the buffer gate just serves as a connection point, because we know that, look, the buffer gate will not change anything. Whatever is going through is whatever is going to bring out. So it is just introduced into the circuit to just cause a natural break within the circuit, as in a break in flow, in order to reduce resistance and then maintain the overall voltage that flows within the circuit. So that is a basic use or importance of of a buffer gate. Okay, so let's continue. Okay, so let's continue and look at our next logic gates. So we also have our NOT gate. Okay, so our NOT gates also accepts one input. Okay, a NOT gate is logically the same as a buffer gate, but the only difference is that it inverts its input. Okay, so if you give it an input, let's say x, a NOT gate is not going to return an x as output. Okay, so when drawing a NOT gate, we draw it the same as a buffer gate, but we bring a zero here or a circle here. The circle here is what represents our NOT. Okay, so it inverts its input. If you give it x, the output is going to be x bar, or we call it x naught. Someone can also decide to write it as x naught. These two are the same. Okay, so if we are to draw a truth table for our NOT gate, we are going to have our input as our x, our output as y. Okay, so if you give it the input 1, what is going to be our outputs? Yes, please, can someone tell us? If we give a NOT gate an input of 1, what is going to be our output?
It will be 0.
0. And if we give it an input of 0, what is going to be our output?
It will be 1.
It will be 1. Okay, thank you, Mr. Kaim. So that is basically the truth table for a buffer or for a NOT gate. Okay, and it's very important that you understand the logic behind how these gates work. Okay, because when you are building circuits, you basically have to be able to import these concepts to them. You see, if you joined the class, you realize that basically we have our lecturer going back to this concept. Okay, along the line, you will start building logic gates. I mean, circuits, circuits, very, very complex ones. And it's very, very important that you're able to understand and apply this concept with ease. Okay, because once you get there, you might not really have the time to come back. That is why I deem it very, very important that we revisit this and really understand it before we continue. So please, even if you can take notes and maybe at your leisure time, go back to it and try to correlate everything so that it sticks. I believe it's really going to help us. Okay, so this is a buffer gate and this is a NOT gate, and this is how they work in circuits. So whenever you introduce a NOT gate into a circuit, it is going to invert or it is going to as in negate any input that it gets. Okay, so if it receives an input of 1, which is the same as true, or which is the same as on, it is going to return an output of what? Off, or false, or 0. Okay, and if it receives an input of 0, which is whatsoever, it's going to invert it and then give us an output of 1. Okay, so I believe we all understand how a buffer gate and a NOT gate works. So we said a buffer gate is used basically to just introduce a natural breakpoint within the circuit. Whereas, what's happening here? What's happening to us? Oh, sorry. Okay, I'm sorry for that. So that's our buffer gate and our NOT gate. So we said a buffer gate basically is used to shorten circuits, okay, and reduce resistance. Whilst a NOT gate is used to invert its input. So if we just want to invert or negate whatever the input is, we use a NOT gate. Okay, so now let us look at the AND gate. So the AND gates, unlike the buffer gate and then the NOT gate, they can take more than one input. Okay, so the AND gate works in a way that, sorry, the AND gate works basically like this. Okay, so if you give it two inputs, please, it can take two or more inputs. So if you give it two inputs, let's say an X and a Y, what it's going to do is that it returns its outputs as X dot Y or X and Y. Okay, so it finds the products of the, it returns the product of the two inputs. Please, when you say product, you are not necessarily meaning times. Okay, times and then and are two different things, though they are similar in their operations. Okay, but they are not really the same thing in all scenarios. So it returns X dot Y. Okay, so this is what you actually mean by this when we talk about and. Okay, so when you have to draw the truth table for and, we have two inputs, right? So our first input is X, our second input is Y. Okay, the rule is that for and, I'll explain why the rule is so. And only returns true when both inputs are true. Okay, so you can have 1, 0, you can have 0, 1, you can have 0, 0, and then you can have 1, 1. Okay, so for the AND gates, the input will only be true or 1 if both inputs are 1. So if your first input, which is X, is 1, and your second input, which is 1, is Y, 1, that is when your output is going to be 1. Aside that, every other scenario will be a 0. Okay, so we have X dot Y or X and Y. This is the truth table for your AND gates, or these are the set of all possible outputs that a two inputs AND gate can produce. So if the input is 1 or true and the output is false, if the first input is true, the second input is false, then the output is also going to be false. If the first input is false, the second input is true, then the output is going to be false. If the third, if you have the first input being false, second input being false, output will be false. But if both inputs are true, then your output is also going to be true. That is the rule for AND gates. And please, let us look at the reason why this is so. So to be able to understand why the AND gates operates in this way, it is very important that we look at how AND gates are built in circuits, okay? Or it's very important to understand the circuit diagram for an AND gate, okay? So let's draw a simple circuit diagram. So we have a simple circuit diagram. We are going to have our transistor. A transistor functions in circuits as a switch. It controls the flow of current. It either cuts it or it allows it flow. Okay. Yes, and then you have the base. Okay. So you have this and then you have the base. Here is the input. This right here is the base. This is the collector and this is the emitter. Okay, please root ahead with the sections. But for now, let me not waste your time explaining transistors, how they work. Second. Okay, please, can I be heard?
Yeah, we can hear you clearly, sir.
Okay. So drawing a simple circuit, we said a transistor functions as a switch. So we can use a switch symbol for a transistor, please. But it's not standard or it's not ideal, okay? So we have a switch right here, okay? Now, take note, when you are using an AND gate to build a physical circuit, you always apply it in a parallel connection, okay, not series. I believe you remember the difference between parallel connections and series. AND gate is parallel, and then OR gate is series. That makes them work how they do, or that makes them function how they do. So you have the first transistor, I said the first input, right? So the first input is our first transistor. This is it. So this first transistor contains our first input. Then we have a second transistor also built here, and that controls our second input, okay? So we have our X here, and then we have our Y here. So we can see that right here, right? And then let's say we can have a bulb here. Okay, so we can have a bulb here, and then maybe we can have our battery terminal somewhere here, okay? Please, this is a simple circuit diagram, okay? And this the practical look of an AND gate. So we have our first transistor, our second transistor. This is how it works, okay? If you look at our transistor 1, which is our first input, if it returns a 1, we said a 1 is on, right? If this, or if our first switch is on and our second switch is 0 or off, what do we think? Do we think that this bulb here will be on or the bulb will be off? Please, I want somebody to give a response and then explain why you think that's the case. We said we have two transistors or two switches. Our first transistor carries our input X in our logic table here. And our second transistor bears Y in our logic table here. We are deciding and we have arranged this in parallel, which is typical for AND gates. And we are feeding it with two inputs, which is this first input here. Okay, we want to see if it is true that if the first input is 1 and the second input is 0 for an AND gate, the output is going to be 0. So let's apply this to a practical AND gate circuit. So if the first input, which is here, the first transistor is 1, and the second input, which is the second, is 0, the 1 means on, right? It means this particular transistor has been connected and power is flowing through it. But the second circuit is 0, which means it is off. Power is not flowing through it. Do we think that this bulb is going to be on or the bulb is going to be off?
Be off.
Okay, so please, what's the reason?
Because it needs to
Please, can you come again? Yes, please. Hello. Hello. Please, can we get somebody to answer this? I think let's try and make this interactive.
Hello, can you hear me?
Yes, please.
All right, so I think it will be off because they are in parallel connection.
Okay. So typically,
since
one good. So if one of our switches is off, that means automatically power cannot flow through the entire circuit, right? So even though this one here is on, okay, and the second one here is off, this off here breaks the connection. That means that once power flows through this place and gets to this particular point, power cannot flow to our bulb. That means that our connection ceases. Okay, so if you use this logic, it tells us that look, if your first input is 1 and your second input is 0, it's still going to be a 0, which is if the first transistor is on, the second one is off, your final results from the circuit is going to be off. The circuit is still going to be in the off state, which is the bulb. Okay, so we say that 1 and 0 is 0. If the first input is 0 and the second input is 1, the first input still breaks the entire circuit. Power will not flow. The answer or the circuit will not be on, which means the bulb will still be off. That means it returns a 0. Okay, so the third one, 0 and 0, everything is off. Power will not flow because the switches are off or our transistors are down, which will return a 0. But if the first is on, we have the power flowing, right? If the second is on, we have power flowing. The state of the circuit is in the on state, okay? Which means power is successfully flowing throughout the entire circuit and the bulb will be on. Okay, so if you go to YouTube and you try to view some practical instances for your various gates, you see they usually use a bulb example to illustrate the gates, and you get to really understand it easier and better how they are practically applied. It's very important that you don't understand it theoretically because IT is not all about theories. Okay, you can just chew that, oh, for AND gates, if your two inputs are true, your output is also true, like that. But you have to understand how they are practically applied in circuits also. Okay, so if both your inputs are in the true state, then surely the circuit is also going to be the true in its true state, which is on. Okay, so that is the reason why your AND gate returns this truth table. Okay, so that is that for our AND gates. I believe everyone is okay with this explanation for our AND gate. We'll try and do the same thing for an OR gate also, so that we don't only understand how we derived the results of those, but we also get to understand how they work in an actual circuit diagram. Okay, but please, I explained again that the actual symbol for a transistor is this. Okay, so we have this, we have that, and then we have a circle here. Okay, where this side is a base, we have the collector, we have the emitter. Okay, please let me briefly explain that. Okay, so basically it works in a way that when you send in an input, okay, or when there is an input signal, if the signal is 1, it releases a very tiny electrical charge, and the tiny electrical charge goes to the base. When it goes to the base, it triggers your how do we call it? The collector. Okay, the collector is the part that stores your electron, or it keeps all electrons. Once your base receives the electrical charge or the tiny electrical charge, it overlays the connection between the collector and the emitter. So the collector can now release its electrons, and then the electrons flows out of the emitter. Okay, which causes electricity to flow freely through through the circuit from one point to another. So that's basically how transistors do work. Okay, so it depends on the input that you give it. That will determine the state of the transistor. So a transistor can either be in the state of true or false, or on or off, depending on the kind of inputs that it is given. So let us get this off the screen and then look at the OR gates. What was this? Please said a second. Okay, so now let us look at our OR gates, how it works, its truth table, and its circuit diagram. So let's take OR gates. Okay. So please, if we can, let's take notes at our leisure time. Revising is the most important key to being able to get these things. Probably you listen to it once, you think you've gotten it. You go back a day later or 2 days after, you might forget. So just do well. In main lectures, subsidiary, just take notes, go back to them, and it will really help you. So let us look at the OR gates, okay? Unlike the AND gate, which only returns a true if both inputs are true, and returns a false for all other possible combinations, okay? An OR gate will return a true if at least one of its inputs is true, okay? So let's look at the symbol for an OR gate, okay? We said that the AND gate, right? I want to establish the difference clearly. When drawing the diagram for an AND gate, this is an AND gate. The sides are straight. Whenever you see any circuit or any transistor symbol, okay, which has this side that being straight, know that there's an AND gate, okay, and then with at least two inputs. But if you have it looking like this, they know that this is an OR gate, okay? So this is how to identify the difference in the gate. This is an AND gate. This is an OR gate. Okay, please, are we cool with that? So whenever you see the first represents an AND gate, the second represents an OR gate. So let's take that again. We have my drawing is not very perfect, but let's manage it like that. Okay, so when you take an OR gate and you give it input X and Y, then the output of that OR gate is going to be X plus Y. Okay. That is the output of an OR gate. If you give it two inputs, the output is going to be the sum of the two inputs. Okay, please, sum does not necessarily mean addition here. Okay. So let's take note of that. The rules are different. Okay, so let us look at its truth table. For the OR gate, we said that its returns are a true if at least one of the inputs are true. So let's look at our inputs. Our inputs are X and Y, right? Let us look at the set of all possible combinations. We can have 1 and 0. We can have 0 and 1. We can have 0 and 0. We can have 1 and 1. And we are saying that for an OR gate, the output is always going to be X plus Y. If at least one of the input is true, the output is always going to be true. So 1 and 0 will give us 1, okay? 0 and 1, 1. 0 and 0, 0. 1 and 1, 1. Why did we get 1 for the first line, 1 and 0? It's because at least one of the inputs are true. Okay, it doesn't matter if the inputs are 3. If at least one of the input is true, you return an output of 1, okay? Here, one of the input is true, the output is 1. No, none of the inputs is true. So automatically the output becomes false. We said we need at least, which is one or more of the input has to be true for the output to be true. But the last one, we have an input of 1 and 1, right? We have at least one input being 1. So we get 1 as an output. So this is a truth table for an OR gate. How does an OR gate work in circuits? Or how did all this come by for an OR gate? An OR gate practically works in circuits that operates in series, okay, or that is connected in series. Let us illustrate that. So you have two transistors right here, okay. So I'm going to use the same symbol for that as a switch to make it easier for us to grasp that, but know that I'm referring to a transistor, okay. So we have this right here, and then we have the second switch also right here. And then we have our power source down here. And then we have our light emitting diode right here, or our LED. So we have this simple circuit connection, okay? We can see that the transistors are connected or arranged in series, right? What does this literally means? If we take the first combination, which is 1 and 0, and we supply the first input, which is 1, to our first, so this is X, this is our Y, right? So when X is 1, or when X is true, our Y is 0, right? What is going to be the state of the circuit? Is the circuit going to be in its true state or in a false state? Please, someone should help indicate that. And then let's know your reason for that. We're having a discussion, please. So does anybody want to give this a try? So we have this set of inputs. Our first input is 1, or our first transistor is in its true state, right? And the second is in a false state. What is going to be our output, or what is going to be the final state of the circuit? Is a circuit going to be in its true state, or it's going to be false? Is it going to be on, or is going to be off? Please, let's give this a try. So please, who wants to try?
It will be on.
It will be on. Okay, your reason.
Because since the first transistor is 1 and the second one is 0, and
Yeah.
it's an OR gate, then it will be on.
It will be on. Look, we have this our power source, right? We have power flowing in this direction. Now we have the power flowing has two options. Either it flows this direction or it flows this direction. This direction is practically blocked because our input is 0. The state of this particular transistor here is that it is disconnected, or it is in its off state, right? And we said that if it is in its off state, there is literally 0 voltage. There is no power flowing through the transistor as at that point in time. Okay, power cannot literally flow. So it means this entire connection here is blocked. But if the flow of current decides to take this particular route here, this here, the state of the transistor is true. So power can flow smoothly because this is connected. So it can literally flow truly into the bulb, which means that we are going to have our bulb being on regardless. Okay, even though one of our transistors is off, we are still going to have power flowing through, which means our circuit will be in its own state regardless. Is there someone want to say something or ask a question? Okay, so please, so realize that if one of the inputs is true, second one is false, we still have 1 as an input. The second case is also true. If X is 0, 1 is Y, we have an inverse of the same scenario, right? This though this is off, power will still flow through Y, and our bulb will go on. But if both circuits are off, okay, let us take this scenario. If both circuits are off, that means power is not flowing at all. Okay, because if both, if both transistors are off, this is what will happen. If current decides to take this direction, this is disconnected, right? If current decides to take this direction, this is also disconnected. What is going to happen? The entire circuit will be disconnected. It will be in its off state. Power will not flow to the bulb. That means that this will be off. Okay, so if it is 0 and 0, our output will be 0. Okay, so if at least one of the input is true, we are saying that current should be able to flow successfully through the circuit. So that is the case, or that is the scenario for an OR gate. And this the practical illustration of the OR gate in a circuit diagram. Please, are we okay with this? Are we okay with this? Shall we continue?
Yes, sir.
Okay. All right. So let me get this off the screen. Okay. So now let us look at our NAND gate. Okay, that is not AND. And how that works. Okay, so our NAND gate is the same as our AND gate, but the difference is that we introduce the NOT gate. Okay, to the output of our AND gate. That means that what? We invert the results of our AND gate and we get a NAND gate. That's basically how a NAND gate operates. So if you want to illustrate a NAND gate, you draw an AND gate and then you add the 0 symbol in front. Okay, please, sorry for the sketch, okay. So if we have the input X, Y, then the output of this circuit is going to be X. We know our AND gate will return X dot Y, right? Or the product of X and Y. Okay. But then we are saying that because of our NOT gate that has been attached to this particular AND gate, we are going to invert the result. And that gives us our NAND gate. Or somebody might also choose to represent this as the inversion of this. That is with this symbol, okay? And it's all the same, okay? So this is our NAND gates, or the how our NAND gate is represented. Okay, so if we want to find the truth table, we first have to represent our input, represent our AND gate, and then invert it, and then we get a NAND. So let me illustrate what I mean by that. So we have our X here, we have our Y here, we have our X and Y, and then we have our X and Y prime. Okay. So if our X is 1, Y is 0, what will be our X dot Y? Or what will be our X and Y? Please come again.
0. 0.
0. Okay. So if we invert 0, what is it going to give us?
1.
1.
1.
Okay. So if our X is 0, our Y is 0, what is going to be our X dot Y, or our X and Y?
0.
0. If we invert it, what do we get?
1.
1. So if our X is 0, our Y is 0, what is going to be our X dot Y?
0.
0.
0. If we invert it, what are we going to get? We are going to
1.
get
1.
1. And if our X is 1, Y is 1, what are we going to get for X dot Y?
1.
1.
1. And what are you going to get for the inversion of X dot Y?
0.
0. That's good. So when it comes to our NAND gates, we are saying that it's just our AND gate, and then we invert the result of that. Now let us look at something about this. Okay, let us look at something about our NAND gates. Okay, so someone can also decide to represent our NAND gate as this. Please, this is a simplified form, and that's a standard form that is accepted. But someone can also decide to represent the NAND gate as this. And then you have your input being your X. Here is Y. And then the outputs of your X and Y, you know this is, and please, you should be able to see a gate and know which gate it is. So immediately you see this, because the bar here is flat, you should know this is an, and it has at least 2 inputs. You should know this is AND. If you see an OR gate, you should know it is OR, okay? So you have an AND gate, so the output is going to be X dot Y, right? So the output here, we can use it to feed a NOT gate in this manner. And that gives us X dot Y prime as our final output. Please, I believe we are together on this. I believe we are together on this. Sorry, I forgot to bring my circle right here. I believe we are together on this. If you remember, we said that this is a symbol for our NOT gate, right? This is a symbol for our NOT gate, right? And this is a symbol for our AND gates, literally. That's this. So now that we found our AND, the output of our AND is X dot Y. X dot Y becomes the input for our NOT gate. And our NOT gate literally inverts the input here, and then we get X dot Y prime as the output of our this particular thing here. So please, in order to be safe, or in order to understand this easy, just stick to the first one, okay? But understanding the expanded form gives you like a broader understanding of how the circuit really works. Okay, so that is that. Okay, so but then there are, let me state one more thing about the, and then we move on. Why is this going this way? Oh, no, I think the problem is from. Oh, what's the problem with this thing? Uh, Sorry, I think yeah. So let's continue. So we can also establish a simple fact here, okay, from this. And this, what I mean, if you have a NAND gate, okay, let me draw this very quick. If you have a NAND gate that has same inputs, okay. Also, at this part of our expression, we have 1 and 1, right? So if you have a NAND gate that has, let's say, same input like X and X, then the result of this particular expression, you know, X and X is going to give us what? X, right? I believe you remember, right? X dot X. That is going to give us an X, right? In the sense that 1 and 1 is 1. 0 and 0 is 0, right? Because I believe you do understand why I'm saying X and X is X. So X and X gives us X, right? So if we invert this, that is going to be X bar, okay? And then if we are using a NOT operator and we give it the same input of X, the output is also going to be X bar. We have X bar as our output also. So you realize that and a NAND gate with two equal or with two inputs that are the same is the same as a NOT gate. Okay, so we are saying that a NAND gate, if a NAND gate has its inputs being equal, the result is a NOT gate. Okay, so a NAND gate with equal inputs is just same as a NOT gate because they all return the same output. Okay, but please, I think this will not be relevant right now. It will be relevant when we get to simplification of logical expressions. So let me get this off my screen. Okay. Just a second. Okay, so I believe we can continue. So we've looked at the NAND gates and then how it works. Okay, so we have other gates as well, like the XOR, which is exclusive or. I think I'll not spend my time on this. Okay, so XOR, which is exclusive or, that one also works in a similar way as our OR, but we said that how OR works is that you at least one of our inputs has to be true for the output to be true, but exclusive or works in a way that you have to have only one of your inputs being true for your output to be true. So when you are dealing with exclusive or, you are going to have 1 and 1 being equal to 0, okay? But then aside that, it works the same as or, and then we have others also. So let us move on for the sake of time. Okay, so let us look at the circuit function, or let us look at circuit functions. We've already looked at the logic gate. So let us look at how we can use logic gates to work simple circuit functions. Okay, so if we talk about a circuit function, we are basically talking about a combination of two or more circuits, right? Like something like A, B, and C, or let's take something like X, Y plus X, Y bar. Okay, this is a simple logical expression. Okay, and you can use this to draw a simple logic gate diagram or a simple like logical block. So how do you use this to draw a simple diagram? You first have to identify the number of gates that you have in your expression. So this is your first expression, this is your second expression. This is your general expression, right? And then here you have your xy here, you have xy up prime here, okay? So if you take this sy, you know sy is the same as x times y, right? Or the product of x and y. And we said whenever we are dealing with products, we are talking about the AND gate, right? So this right here is our AND gate. And whenever we are talking about sum or plus, we are talking about our OR gates. So this right here is our OR gates. And when we are talking about here again is x dot y, okay, that means we are talking about our AND gates. So we are going to use three different logic gates here. I mean, two different logic gates here, the AND and then your OR. Okay, but then the main diagrams are going to be three because you have the first, you have the second, and you have the third. Let me illustrate what I mean by that. So when it comes to x or y, which is x and y, okay, we know that this is how our AND gate looks like, right? So here we have two inputs. We have x and y, right? So our first input is x and our second input is y. What output is it going to give us? This x and y. So that gives us this right here, which is x dot y, right? And then now the result from this right here becomes an input on its own. And then we have the second equation being, okay, so let's talk about the or. We have and or. Let's do it. The or right here is an or gate, right? It's an or gate. So let's represent that. So this is an or gate right here. So the first input is our x and y, right? And the second input is our x and y prime. So let us represent x and y prime. X and y prime is also an AND gate. So this is an AND gate. We have first input as x, second input as y prime. Okay. And then the output of this is going to be what? X dot y prime. We all agree with that. This is an AND gate. So an AND gate, the output of x and y prime is going to be x dot y prime. Okay, and this becomes our second input that we are going to use to feed our OR gate. So the first input for our OR gate is x dot y, right? And the second input from this side is our x dot y prime, right? So we have our x dot y prime. Okay, so what output is it going to give us? We know this is an OR gate, right? So x dot y or x dot y prime, how do we represent it? You know, or is the addition symbol, right? So we are going to have our output being x dot y plus x dot y prime. We can all see that we have the first input being x dot y, second input being x dot y prime. And if we use the OR logic gates to process these two inputs, we are going to get x dot y plus x dot y prime. And we can see that our final output is the same as the logical expression that is above here, or the logical function that is above here. So this is how to use your expression to draw your logic gates, or this is how to draw the logic gates for your expressions, okay? And you can do this for every expression given. In fact, the reason why you have to understand how to simplify logical expressions, as we're doing in our last lecture sessions with our last lecture session with our lecturer, okay, is that sometimes you are giving this expression and the expression is very long, but then actually you can simplify the expression in order to save more transistors. Imagine you having to use one transistor for this, another for that, another for this. You have three here, right? There are some expressions where you have to use about, let's say, 50 different gates, okay, to form your how do you call it? To form your transistor, to form your circuit, okay? So if you have, let's say, 20 or 50 different gates, and the expression can be simplified to only 10 or 15, you might want to simplify it. So this is the purpose why simplification of expressions become very important, to save transistors, okay, and to make everything look much easier and simpler. So if you don't know how to convert expressions to your diagrams, then you have to really start mastering how that is done, okay? So let us take another example of how this is typically done. And then we are going to take questions on this. I think for me, if we even end with an understanding how this works, okay, how to convert your diagram to expressions and how to convert your expressions to diagrams, then basically we've solved a very, very huge problem. So from there, we can look at how to simplify expressions, how to find, and to simplify expressions, you use two basic methods. You can either use your kernel map or your K-map, or you can use a various logical identities or various Boolean laws, okay, to simplify your expression. So once you understand this, you can now look at how to simplify expressions. And after you've been able to understand how to simplify expression, you can say that majority of our headache is gone. Okay, and we've now gotten the basics for Dcit 203, and after that we can be able to build whichever concept we want to build out of this. So let us look at another example or scenario for that. I think for this, let's make it very, very interactive. Let's all do it together, okay? So we are going to give ourselves a much more complex expression. That means that you have to all follow thoroughly, okay? So that at the end of the day, everyone understands what we just did. Okay, so let us take the expression let us take the expression, which expression should we, what's even causing this? Okay, that's better. So let us look at the expression, let's look at A plus B and then A B prime. Okay, let's try and draw a diagram for this simple expression. So if we remember the last method we used, we said that the first method is to identify the number of gates we are going to use, right? So can somebody tell us the gate we are going to use for this particular expression? We have A plus B. Please, which gate are you going to use for this?
All gates.
And all gates.
Okay, so that we are going to use an OR gate for that. That's very correct. So we are typically going to draw our OR gate. So this is our OR gate, and our inputs are 2. So we have A and B, right? So that means that the output we are going to get from this is going to be A plus B. Okay. So we have another expression here, right? But before that, we should know that this is in bracket. So if this is in bracket, that means that automatically what is unifying this here and this here is a multiplication. It's a silent multiplication, right? So we should remember that right here, you also have something else here, right? Let's not forget that. But then let us look at the other side of the whole thing. So we have AB prime. So please, which logical gate are you going to use for AB prime?
An inverter gate.
Please come again.
An inverter gate.
Okay, so we are going to use an inverter here because of our B prime.
Okay, for all of AB. Sorry, an AND gate. AND gate to connect A and B.
Gate.
Sorry. Yeah, sorry.
Perfect. So an AND gate right here for our A and B. Okay. So we have AND gates. We have our A here. We have our B. Oh goodness. We have our B here. So our output here is going to be what? We have B prime, sorry. Forgive me. So we have A, B prime. And which gate is connecting our two expressions? Let's look at that carefully. Which gate is connecting our two expressions?
An AND gate.
An AND gate, perfect.
And
so we have an AND gate connecting our two expressions. So we connect our two expressions using an AND gate, right? And the two inputs becomes A plus B and A B prime, or A or B and A and B prime. So that gives us a final output of what? A plus B into brackets dot A B prime. Or we can decide to take the dot away, still same thing. Okay. So please, I hope we are all together on this. In case you did not understand how we did this, that's the very reason why you are here. So just voice this out and you would begin everything again. So please, is there anyone here who did not understand what we just did? Mr. Kanye.
A little bit confused about the second input.
Okay, so let us go back to that. So please, we said when you take
the second
this
input, yeah,
okay, that is this, right? Okay, so
the AB.
okay,
I
so
can't
the AB.
I can't see the invector over there. So
okay. The reason why we did not use a NOT gate here is because you see the prime here only affects B but not A. Okay, when we are looking at, you see this is A, B prime. When we are looking at the gates we are going to use, we are looking at which gate is processing. You see, this is an input. Oh, this is one input. This is another input. Okay, so we have a gate right here that is processing two inputs. This first one and the second one. How do we know the gate? The gate is what is actually connecting to these two things together, or these two inputs together, or that's what is processing the two inputs. And what is the gate? It is at times, because you know mathematically AB is the same as A times B, right?
Yeah.
So AB prime is the same as A times B prime. And we know that in IT, when we are talking about times here, we are talking about, or when we are talking about product here, we are talking about the AND gates. Okay, so that's the reason why we use the AND gate for the second input. So we can call, in the bigger picture, we can call this input 1. We can call this input 2. I think gradually we'll look at other concepts that explains the different type of inputs that we can have in expressions. Okay. But this becomes our input 1, this becomes our input 2. But then when you come to input 1 itself is a gate on its own. And input 2 on itself, input 2 on its own is also a gate on its own. So we're able to know the kind of gate this one is by identifying what connects our two inputs here. And what is connecting it is our plus. And we know the plus is our OR gate. That is why we use our OR gate here. And now we come to look at the second input. So in order for us to look at the kind of gates to use, you have to look at which kind of logic connects these two inputs. And the logic is product, right? Which is our AND. So that is why we used our AND gate here. So we basically have to just look at which logic is connecting our inputs. So we know that the first input is A, the second input is B prime. Here, the first input is A, second input is B prime. And when we process this, we know that all those two bigger inputs are connected also by what? By multiplication, right? Or technically, they are multiplying each other. And multiplication or product is also AND. So it means that the kind of gate which is connecting these two gates here is an AND gate, okay? So that means that the final answer will be the AND operation for this right here and this right here. And for us to perform an AND operation, you have to use an AND gate, right? That was the reason why we use an AND gate here. So we feed it with an input. This is the first input. So we feed it with the input coming from here, and then the second input coming from here. And that gives us our A plus B, AB prime. Please, I believe we are We are okay. Or someone still has a question.
Yeah, I was expecting some invector like at the AB prime side. I was expecting some
Okay, sir.
not sign
So
over there.
you would have used an inverter if this was to be like this. Okay, so we have some, if we would have had something like this. Yeah, okay. Meaning that this inversion symbol affects both the A and B. I don't know if you are getting me. So
Yeah.
if, yes, sir.
Yeah. Okay.
So if this was to be in brackets, then 100% we would have used a NAND gate right here.
Okay.
But because it was only affecting only one input, we cannot use a NAND gate for this.
Okay. Thank you.
So please, you are welcome. Sir. So please, are we together? Are we together? Okay, so if everybody is cool with this, then let's try something more complex. Okay, let's try something more complex. And with this, we are going to introduce another concept altogether. Okay, that is a POS and an SOP expression. I believe you already know that. That is a SOP and then a POS expression. Okay, so let us take a typical SOP expression. Okay, so we have the expression SOP means sum of products. Okay, so we have XY plus we have X. Should I use X bar Y or I should use XY bar? Let me use X bar Y plus Y bar Z. Okay. So the reason why we are saying this is an SOP expression. Okay, let me use this expression to explain what an SOP expression is. I believe when you get to the Cannon map or the K map, you start seeing these things, and then your mean terms, your max terms, your sub terms, those terminologies come into play. Okay, but we have to build it on from somewhere. So let us look at your sum of products. So sum of products is basically this. You have different expressions, okay, being worked together with the sum operator. So this is a different expression, x times y. This is a different expression, x times y bar. No, x bar times y. Okay, let me draw this. Let me write this clearly so that it doesn't confuse anyone. So you have x times y, you have x bar times y, and then you have y bar times z, okay? So these are different expressions, but there is one particular operator that is bonding all this, that is bonding the three different expressions, and that operator is the sum operator or your addition operator, okay? So that is the reason why we call this sum of products. So you have the product of x and y, the product of x bar y, and the product of y bar z, okay? And you are summing all the products together. That is why we call it a SOP expression. It's just as simple as ABC, okay? So we give it that name because that is a kind of operation that is being performed. We are summing all the products. That is why we call this type of expression an SOP expression, okay? So please let us do well to understand things in this manner and these terminologies and how they work. So when you are calculating mean terms, for example, or when you are finding our mean terms, you find mean terms on SOP expressions, okay? We have other expressions also like POS expressions, which is our product of sum expression. And that one, you don't find mean terms, you rather find our max terms, okay? So now let us just stick with SOP expression. Since we now know what SOP expression is, we said that they are basically an expression, okay, that involves the sum of the products of different expressions. Okay, so we have the product of this, that, and then we are summing them together. So this expression, we can call it an SOP expression. Okay, so let us move forward. Now let us draw a diagram for this particular expression that we have here. Okay, you realize that this one is a little bit more complex than the previous ones that we've done. Okay, so to do that, we'll start from this end. So we have our x, y. So our xy, which logic gates do we think we are going to use for our x, y, and y? Please, can someone help us out?
So we are using the AND gate.
Perfect. So we are using the AND gates because this here is x times y. And you know that when we are dealing with the products of two inputs, we are talking about the AND gates. So we have x here, we have y here, okay? So we will just take the outputs of this to be what? X dot y. And then the second expression, what are we going to use?
AND gate.
We are going to also use an AND gate, perfect. So we have another AND gate. The inputs are also 2, okay? Please, there are different ways to do this, okay? Someone can just say that, okay, here is we have x prime, okay, or x bar, and then y. Someone can say y is already here. So he's just creating a connection. Please, this affects you too. You are dealing with wires. So you can directly. So these are live connections, okay? So you can decide to connect this particular input here directly to this. And it becomes a valid input as y for the second one. But please, if you don't want to complicate things, you can just decide to repeat your y again, okay? So x bar y, okay? Or if you decide to also connect y to this, it's also valid regardless. Okay, and then the output of that is going to be what? So we have what? X prime y. And then our third one, which logic gate are you going to use?
AND gate.
AND gate again. That's perfect. So we are going to use a third AND gate. We have X here, right? No, we have Y bar, sorry. We have Y bar, you have Z. And then please let me get this off so that it doesn't confuse anybody. So this right here gives you what? Y bar Z. So now we have 3 different inputs, okay? Now, which operator is processing all the three inputs that we have.
The OR gate.
The OR gates. So we are going to draw an OR gate for all our three inputs. I said earlier that the AND gates, the OR gates, they can have more than two inputs and they can still process them. Okay. So the final output is going to be what? We know our OR is just the addition symbol, right? So we have X, Y, or X bar Y, or we have Y bar C. And then we've been able to successfully draw a diagram for this expression or function right here. Okay, so please, I believe we are okay with what we just did, or someone has a question so that we talk about it. Please, anyone with a question? If you're also confused, just let us know and we'll take it again.
Please, can you take the SOP that side again?
Okay, that's the explanation of the SOP. Vida.
Yes, please.
Okay. So I'll do that.
Noted.
Okay, so Mr. Richard.
Yeah, senior, please kindly take over it for me, okay?
Okay. I think the important thing here is that everybody is able to understand. So we cannot move forward if we've not really gotten it. Okay, so let me please, can somebody write down the expression? I want to clear everything and then we start again. Can somebody write down the expression, please? Please, does someone has the expression?
Yeah, you make it.
Okay. All right, so we had x
XY
xy, okay,
plus X bar Y
x bar y
plus Y bar Z
plus y
bar Z.
bar z. Okay. So thank you, sir. So first of all, I use this to explain what an SOP or what a sum of products operation is. Okay. So this is what we mean by a sum of products operation. Okay. So we could see that there are various expressions in this expression. Okay. So if we take xy is an expression on its own. Okay, x bar y is an expression on its own. When I say xy, I mean this. One, these are first input. These are second input. These are third input. Okay. But within this input, we still have two inputs there, which is x and y, right? So these two inputs is an expression on its own. We can draw a logic gate for it differently. Okay. This x bar y, we can draw a logic gate for it differently. And this x bar z, this y bar z, I mean, we can draw a logic gate for it differently. So they are valid expressions on their own. So you can see that we've taken three different expressions and we've brought them together, okay, using an OR gate. And how do we know this OR gate? Or these three expressions were brought together using an OR gate? It's because of the addition symbol, okay? So immediately we see the addition symbol bonding these three expressions, we know that, look, they were brought together with the OR gates, okay, which is typically a sum or the addition of all the three individual expressions, okay. So we are summing all the three expressions together, okay. But then if you look at each expression is actually a product term, okay. Each expression is actually a product term. What do I mean by a product term? It's because you have two different inputs being brought together with the AND gates, okay, or two expressions being multiplied together. That's x times y. So this one right here is a product term, okay. And we also have the sum term. So this is a product term, okay. So this right here, xy, is a product term. This right here is also another product term. So three different product terms are being brought together or are being summed together. We have an SOP formed, okay? So an SOP or a SOP expression is basically formed when we add or when we sum the products of different expressions, okay? So this is our first expression, second expression, third expression. They are all, they were all brought together I mean, using the AND gate, or we found the product of x and y, and we had xy right here. So we call it a product term, okay? So please, from now, when I use a product term, I'm talking about an expression that was brought together if you have something like x plus y, we call it a sum term. Please can please can you hear me?
Your line is
Yeah, your line was breaking up for a little, but it's
I
okay
think
now. It's
yeah,
okay now.
someone. Okay. I had a call, that's why. So if you have something like x plus y, we call it a sum term, okay? A sum term. If you have x, y, we call it a product term. Okay. And if you have a sum term or product term that contain all variables of a logical expression, we call it the I mean, if you have a sum term that contains all the members of a, I mean, of the expression, okay, of a logical expression, we call it a mean term, okay, but please, we'll come there, okay. So please, x plus y is a sum term, xy is a product term, okay. So when I say a product term, this xy here is a product term. This x bar y is also a product term. This this y bar z is also a product term. Now, these three different product terms have been brought together or have been summed together, okay? So the resultant of the operation is called an SOP expression. Please, I believe we get that. So when we sum the products of different expressions together, we get an SOP expression. So that is what an SOP expression is. Vida, are you okay? Or I should take it once again.
please, I'm okay. Thank you so much.
Okay. So let me give one more example of an SOP expression. Okay. Please, this is to familiarize ourselves with the terminologies, okay, so that going forward, they would pop up again. It doesn't become foreign, or it doesn't look foreign, okay. So if we have, let's say, zy, zy is technically z plus y. This is a product term, okay. You have another operation, you have yz. This yz, xy, I mean, is technically x times y. And then let's say you have x bar, y bar. You are getting that. This is also a product term. Why? Because they are all multiplied together, okay? If we decide to add all these three together, okay, we are going to get what? X, Z, Y, right? I think I had a network disruption, plus X. This gives us an SOP operation. Why? Because we've summed the products, and we've summed the product of different expressions, okay? So when we sum the product of different expressions, we get an SOP expression. Please, we are cool. Okay, so that's an SOP expression. And let me differentiate that from a POS expression, that is product of sum expression. So this same thing, if you have x plus z plus y, okay, this is a whole different thing altogether. So if you have z plus y, x plus y, and then x bar plus y bar, these are all sum terms, right? Because you have they are all sum operations, okay? There is no product operation here. But if we decide to find the product of the sum of all these operations, so if we decide to find a product of all this, we are going to get z plus y, right? Brackets x plus y, brackets x bar plus y bar. Okay, this thing that we've done here is a POS expression. Why? Because we found the product of the sum of these individual expressions. Okay, but when you find the sum of the product of the individual expression, you get a SOP operation, the post product of sum. So just that is basically how it works. Okay, please, if you're able to understand how it works with alphabets, then when we get to the ones and zeros, they become very direct and simple. Okay, so let's continue. Okay, so we said we have three different how do you call it, expressions, but then they are brought together or they are summed together, right? So let's draw the diagram for this. Okay, so we have, I believe, has anyone attempted drawing the diagram?
Mr. Isaac.
Yes, sir.
Yeah, sorry, please. My hand has been up for a while now, but since we're not calling me, I was already fine. Just try this.
Okay. So I think I wasn't really seeing the screen.
All right. So just a little question. You see,
Okay.
it's possible to like simplify some of the expressions. Possible to simplify them further. So my question is, if a question is given to you, the lecturer expects an output. Okay, I don't know. I know you don't know the lecturer's mind, but if you simplify it further and you draw your logic gates, per definition, it should be correct. Will it be recognized as correct as someone who just drew it from the raw expression as well?
Exactly.
Yeah.
Exactly. In fact, the standard way to go by such question, or I mean, the standard way to draw your diagrams for very complex operations is to first make sure that they are simplified to their simplest form. Okay, so after this, the next thing we're going to look at is simplification. So you have to be simply, sometimes the expression can be very, very, very complex, but then you realize that no, this thing can just be something very, very direct and simpler, much simpler if they were simplified. Okay. For example,
That's right.
let us take an expression like let's take 3 input. Okay, so X, Y, and Z. You are asked to draw a diagram. You have, let's say, X, Y, Z prime, okay, plus X, Y, Z plus X bar Y, Z, okay. When they ask you to draw the diagram for this, you might go straight forward and start. You see, the problem is, or the whole thing here is that we are not looking at a diagram for its sake, but a diagram that returns a valid output. Okay, so if the output of this whole diagram is, let's say, when given a particular set of input is 1, okay, after simplifying it, if the output for those same set of inputs is still 1, then it means that this particular expression here and its simplified form are going to perform the same function in any circuit. But with that, we are going to need much lesser gates to implement them. And everything is going to be much lesser, simpler. You will need much smaller space to be able to implement that particular logic. And it becomes much easier to work around this. So let us see if we can simplify this further. Okay, so to simplify this further, let's see. We can, this right here, I think we can have X, Y, right? Please, if you want to really understand the simplification, you have to go back to understanding the Boolean laws, okay? The various laws, the identity law, absorption, I mean, all those things, you have to very much understand them. And then, I mean, they are laws, okay? You don't have to really stress yourself on understanding how they came into being, but you really have to understand them and have them at the back of your fingertips and be ready to apply them whenever any question or a problem is given to you. Else, when it comes to the simplification, you get lost. Okay. So you have X, Y. We can factorize this out, and then you have Z prime plus Z, right? Please, are we right? Because if you open this, you have X, Y, Z prime plus X, Y, Z. So we have this plus X bar Y, Z. So let's see if we can do something to this. So X prime plus Z, okay? If you remember, we said A plus A prime is equal to what? 1, right? And A times A prime is going to give us what? 0. Please, please, do you remember this? This thing
Yes,
right here.
Yeah,
yes.
the
Exactly.
identity laws. Yeah.
Exactly. So we can be able to import this particular law right here. That is A plus A prime is equal to 1. So we have Z plus Z prime being 1. So this becomes 1. So we have X, Y right here. If you perform an AND operation right here, that is X, Y, and 1, the final answer is going to still be X, Y. Okay, so there is no need to even, and let's just prove that you have 1.1, the final answer is 1. Okay, 0 dot 1, I'm coming. Your final answer is 0. Yeah, so literally the input returns the same output. So X, Y times 1 gives you the same X, Y. Okay, please not necessarily times. Plus, you have what again? X bar Y Z. So here, what again can we do? Let's factorize. Let's bring.
Y.
And what do you think we should? Yeah, we can have X bracket. Let me see.
No, let's factorize Y.
No, Y bracket X plus
Plus X bar.
X bar Z, right? And please, you all remember the distributive rule, right? So the distributive rule says that if we have a scenario like this, that is, we have A plus AB is the same as A plus B bracket A plus B. Please do recall that. So this gives us Y into bracket X plus X bar bracket X plus Z. Okay, so we know X plus X prime repeats this particular law here. That is A plus A prime is equal to 1. So X plus X prime is also going to give us 1 right here. So we are going to get Y bracket X plus Z. Okay, and that means that this is going to be X, Y plus X, Z. I think from here, we cannot do anything about this again, right? So we have XY plus XZ, okay? So if you check the original problem setting, you would have needed, let's count this, okay? 1, 2, 3, okay? So assuming you use an AND gate that accepts 3 inputs for this, another AND gate that accepts 3 inputs for this, another AND gate that accepts 3 inputs for this, you would have gotten 1 gate, 2, 3, okay? Plus, if you are done, you have to combine all of them using an OR operator because of the plus symbol here. And if you use the OR operator, that becomes another additional 1 gate. So how many gates are you going to use in total to implement this expression? That is 4. But after simplifying like this, we have XY plus XZ. And then if you give it any, or if you feed it any set of input, it's going to return the same output as this here. Okay. I mean, the question here, okay, providing you do your simplification right, the simplified form should return the same output as your main expression, which means that it can perform the same function as you drawing the complex circuits for this particular diagram. So here you use 4 gates. But here you are only going to use just one gate for this, one gate for that, and another gate for this. That is 3 gates, okay? And each of your gates here is going to have just 2 inputs. But if you use the original form in the problem or in the question, each of your gates are going to have 3 inputs. Everything is going to look very messy and complicated, and it's not standard. Okay, it's not standard in a way that assuming that, and then every single transistor you are going to build on the circuit, you are going with the complex form. Imagine everything will look so messy and difficult to interpret. Okay, but if you simplify it to its simplest form, it becomes very easy to work around everything. It saves space, it saves time, it saves you money. It's just the standard way to go. Okay, so simplification, you really have to understand how to do it. I think our time is almost up, so we might not look at simplification today, but our next session, we look at simplification using the canal map or the K map. And then we're also going to use that we're also going to look at simplification using the Boolean laws as well. Please let's return to drawing a diagram for this, and then we close. So I'll give you one to go and try, and then we can end the session. So please, the problem set was what? We had XY, right? I think it was 3 SYs by different ways. Please, can someone repeat that again, please? So was the second S bar Y? I think S bar Y, right? And the third was what?
X bar, Y bar.
X bar, Y.
Okay, so X bar, Y bar.
That's right.
Okay, so let's have the diagram for this. So having the diagram for this, we would have our first input, second input, we have our third input, right? So this particular operation here, or this particular expression here, which gate are you going to use to draw that expression?
And
The
And
AND.
exactly. So we are going to use our AND to draw this particular expression. So we have our input are 2, we have X, we have Y. So this gives us an output. Then we have an output of X, Y, right? And then the second one also, which gate are you going to use?
All these.
and gates.
The AND gate. We have X, and then we have Y. No, X bar. And then we have Y. This gives us X by Y. And then the third one also, what are you going to use?
And
We're also going to use our AND. I think some people will be confused with using the NAND. But you see, the whole thing is that you have to look for what is bonding. Is this X bar times 1 Y bar? So far, it's X bar times 1 Y bar is AND. So these are 3 AND. That's why we call it a valid sum of products operation, because each gate in the expression is AND. And then this gives us the output X bar, Y bar, and we literally unite them with what? Please, which operator are you going to use to
all.
the
all
OR gates? That's very cool. It's okay. And this is going to give us a final output of xy plus x bar y plus x bar y bar. And then we have our diagram drawn right here. So please, any question with this diagram? Is there any question with this diagram?
No, please.
Okay. So please let's take this expression and then let's try it on our own. It's very, very complex. But if you're able to work this out, then I think you can be able to hit your chest and say that now you are. Oh no. Let's make it this way, okay? Let's rather take a diagram and then we'll try to deduce some expression out of the diagram. Okay. So let's see if we can be able to identify the various type of gates by looking at it and be able to work our way around getting a diagram out of it. So let's take an illustration first, okay? So illustrating this, let's say we have our input as A, B, maybe we have a third input as C. Let's see. This comes together and then gives us this right here. So how do we draw or how do we deduce our expression out of this diagram? First of all, you can see that this here is AND, right? And please,
Yes,
which
that's
gate is this?
fine.
This is all right.
All day.
So we know that this is A and B. So how do you write that? This is A and B, right? And for C is a single input. Okay, so C, we pass on the input to this place. So it means that the inputs here will be what? A dot B, and then the input here will be what? Will be C. So we are performing the operation A dot B, and our second operation is C using the OR gate. So A, B, or C. How do we represent this? We have A, B, or C. We have our expression for this particular operation. Okay, so let's take another diagram. Let's take something a little bit different. So we have X here, we have Y here, and then let's say this comes here. Let me repeat the same thing for the input. So we have Z, okay. So, and then let's have one more. We have X bar. And then let me see, this input comes down here. This comes down here. And then they are joined together by this right here. And then let's make it a little more complex. Let's add a third right here. And let's give these three different inputs. So we have X, we have Y bar, and we have Z. Okay. So we have the output of this and the output of this coming together. Okay, and let me add one more here. So here is W. Okay, coming together. No, let me change this. I've used too much of this. So let me change this to something different. Let's use this right here. To write a function or expression for this diagram. Okay, so please, we can give this a try. So when we meet again, this is the first thing we are going to solve this quickly, and then we move on to looking at our simplification using Canal maps, and then the how do you call it, the Boolean laws. Okay. So please, one person should draw it neatly, take a picture of it, and maybe put it on the platform, so that the others would also get to see it and be try their hands on it also. But please, do give it a try. If you're able to work this out, then basically you've understood how to build your circuit diagrams or your diagrams. All right, please. Let's allow a minute for the drawing of this, and then we'll move on. You can close.
Yeah, so it's on the platform.
Okay, sir. Thank you very much for that. So please, if you are not done drawing it, our boss has helped us with that on the platform, so you can look at that and then. Okay, so please, any question at this point? If there is none, then we can bring the meeting to closure.
There is no question.
Okay, please. And thank you very much for making it for tonight's session. So we are going to meet for the next section again. Okay, so I'm ending the meeting.